So today I have the honor of introducing Mehdi Moussaid. Mehdi comes from a very interesting and interdisciplinary background. He has an engineering degree in computer science and a PhD in cognitive science. In addition, he has worked in both cognitive science and biology labs. In 2011, Mehdi joined the Institute as a postdoctoral fellow with the ABC group. And in 2013, he started a position as a research scientist with ARC. Mehdi's interdisciplinary background is reflected in his research in the use of simple heuristics in crowds, which includes work on pedestrian behavior and management of pedestrian flow and how to prevent crowd disasters, as well as collective behavior in psychological crowds. His talk today will focus on the use of simple rules that pedestrians employ in crowds.
So thank you very much, Kathleen, for this very nice introduction, and thank you all for being here. So today I will talk about the behavior of pedestrians and the collective dynamics of human crowds, right? So this is about how people navigate in a crowded place, how they move in a crowded place, how pedestrians interact with each other, how they influence each other, how they imitate each other, how they avoid each other, and how repeated interactions between many people give rise eventually to collective patterns at the scale of the crowd, right? So this is a pretty interesting problem because if you think about it, navigating in a crowded place, it's a pretty complicated, pretty complex cognitive task, right? So you have on the one hand to pay attention to your physical environment. So you have to collect information about where are the walls, where are the static obstacles, where are the exits, where do you want to go, how are you going to get there. Sometimes you need to look at the signs on the walls just to get your way to the exit and things like that. But on top of that, even more complicated, you need to pay attention to your social environment, right? So what other people are doing. As this video illustrates, it's an amazingly complicated task. So basically it's a dynamic environment, a moving environment. So you need to look around, where are your neighbors, where they are moving, and you need to anticipate where they will be in a couple of seconds, given their position and their current movement, such that you can avoid upcoming collisions with other people, right? And find your way to the exit. And you have to do this continuously, right? And you have to adapt your walking behavior almost in real time, like precisely in real time if you want to avoid collision. For sure, any computer or any robot would have like a very hard time to do this, and I don't think it's possible in current state of technology. But however, people, we do that pretty easily, right? We don't even have to pay full attention to what's going on. We can even like talk to a friend on the phone or send a text message, and collisions between people are extremely rare. So how do we do this? How do we process such a huge amount of information in real time in such an easy way? So that's on the one hand. On the other hand, the other question is, what kind of collective behavior does it generate, right? So just to give you like an appetizer, there are different things we can study. We want to know, for example, why and how congestions happen, for example, in crowded subway stations, and how can we avoid them also. But even under normal traffic, under normal conditions, we want to know, okay, how does the traffic self-organize? How do people move, and how can we maybe adapt the surrounding environment in such a way that we could like enhance the walking comfort, like making smarter places for our daily walks. And for sure, the most impressive kind of collective patterns are also about extreme densities, so that like mass events when you have a huge number of people gathering at the same place at the same time. Here you have two examples. The first one is the Muslim pilgrimage that happened in the Mecca every year, which is one of the biggest crowd gathering where accidents happen, unfortunately, almost every year. And I will show you some more videos of that later. And this is just another example, like a casual aggregation of people. This was in Washington, the crowd in Washington during Obama's speech. And in fact, as a matter of fact, I mean, things tend to get a bit worse these days, as you can see from this chart. So over the last 40 years, as you have here, what you can see is that not only the circles are increasingly high, which means the number of incidents reported tend to increase, but the circles are also increasingly big, which means the number of fatalities is also increasing, right? So not only the accidents become more frequent, but they also become more serious and more deadly, so to say. Okay, so that was just the general background of my thing. Now, if you want to understand crowd behavior, we need to do like a bit of theory about complex systems, because a crowd of pedestrians is a typical example of a complex system. So what is a complex system? A complex system is something that is made of a large number of individuals, okay? So in that case, we think about pedestrians, but it could apply to other things. A large number of individuals. And in such a system, each individual behaves according to his own motivation, right? So I want to go from one point to another, and I want to walk at my comfortable walking speed. Might be slow or fast, never mind. So I want to do my own things. This is the micro motives that Ralph was talking about a couple of days ago, last week. However, by doing so, I'm more or less influenced by the behavior of people around me, right? So for example, if I'm walking in the street and for some reason the person in front of me slows down and stops, then I have to slow down and stop in turn because I want to avoid a collision. So in fact, in that particular situation, I have adapted my behavior to the behavior of my neighbors. Right? I don't really know why, but I do it, right? Because, okay, so there's a change of behavior depending on what others do. And the fascinating thing is that the neighbors are themselves interacting with their own neighbors, and the neighbors with their neighbors, and so on and so forth, in such a way that the full system constitutes like a complex network of interactions where little perturbation, little something is likely to propagate from one person to another, giving rise to collective patterns, right? And the complex system is also complex because if you want to predict how one particular individual will behave, you need to know how the neighbors behave. And therefore you need to know how the neighbors of the neighbors and how the full system behaves, right? But if you want to know how the full system behaves, you need to know how the individual will behave in there. So there's something tricky here in the understanding of the system, which is also what is interesting in this study. So the key, I tell you now, the key to understand a complex system is what we call the interaction law. So the law of interaction is basically how does one person change or adapt his behavior in response to the behavior of his neighbors. If you know about this law, then you can build up computer simulations and apply the law to all of the individuals and see through simulation how the group behave and then make the connection between the individual and the group. And one thing that I personally believe is that those interactions between people can be well described by means of simple heuristics, which is not always the case in current literature. I'll show you one example. So this is a study that we did recently in the train station. It was not a research study, it was more like a consulting study. But basically we did some analysis of the flow of commuters in the train station, right? And so we measured like a lot of things like the average speed, the average density levels and things like that. But we have observed one particular collective pattern. We have observed that there were, in that particular train station, there was an unbalanced exit usage, in the sense where one exit was very much used by a majority of people and almost systematically congested, which was a problem, while another exit, not that far away, was always underused and almost empty all the time. But those two exits had rather the same value in the sense where they both take you to the outside, right? So why do everyone go to one place and just forget about the other one? This doesn't look rational, right? So if you want to study this problem from the point of view of a single individual, right? You may say, well, I assume that one commuter would get out of the train, right, and would collect information about the environment. So where are the signs? Where are the exit signs? And then after collecting and processing all the information, then evaluate each option, which exit is the closest one, which one takes me to my favorite place, and then choose an exit. Well, balancing these two choices, I go to the left side, right? So that's how one may analyze the situation. It turns out, to my opinion, this is not how things happen. At least this is not what I do. What I do when I get out of a train in a place I've never been before is I just look around, I find a few people and I just follow them, right? And I bet that one of them knows where he's going and will take me to the closest exit. And this works very well, right? So I always end up at the nice exit. So this is a good strategy, right? Look around and follow your neighbors. It's a very nice strategy. You don't need to spend like a couple of minutes collecting your own private information. You just bet that others will take you there. The only problem is if you have too many people and if most of them use the same heuristic, right? So in that case, people will start maybe to follow me, right? But I don't know where I'm going because I'm just following someone else, right? And maybe that person doesn't know where he's going neither. And if you have these rules that apply between people and repeatedly, what happens is that the majority of people will end up in the same exit. Not all of them, because some of them have private information. Majority of people will end up at the same exit, and the minority in the other one. And the more people you have, the bigger is the majority that end up at the same exit, because you have a strong amplification. And this is how you can explain this unbalanced exit usage, just by injecting a small proportion of imitation. Therefore, it's an interesting heuristic here. Look around and follow the others, because at low density, when you don't have too many people, it's a good strategy, because you will end up in a nice exit. But when you have too many people, it's a bad strategy, because you will end up in a place that is congested. So it was better to go the other way. So depending on the social environment, it might be good or bad. I have 2 questions already.
Yeah, how is that similar to herd behavior you see in stock markets?
Conceptually, it's the same thing, right? So you have certain portion of people who imitate and another one who have their own private. And the dynamic of the system is a matter of those proportions, whether majority of people will follow and then you have herding, or whether...
so is that then kind of a bubble? So everyone wants to the same exit, and the other one is not used, and eventually it's going to burst. You
can call that a bubble, yeah. I mean, we can't push the analogy too far away, but conceptually it's the same problem. Okay. So that was one possible kind of simple heuristic that you can find in crowds. What I want to say, like we'll do in the next 15-20 minutes, is that there are different natures, different types of interaction in crowds, right? Imitation is just one kind, but you have a lot of different kinds of interactions. So I would like to review just a few of them and show you what could be the connection between those simple heuristics and collective patterns, right? And then I will talk about modeling. Okay, so multiple natures of interactions. So there are different kinds of interaction. The first one I'd like to talk about, so it's not about imitation, it's something else, it's about collision avoidance. Okay, so this is again another kind of interaction. So you actually change your behavior based on what others do, but you're not trying to imitate, it's rather the opposite, you're trying to avoid those people, right? So it's collision avoidance. And in that case, well, basically, you collect visual information about where are the other people, and the consequence is a modification of your walking direction. So if this person was not there, this one would follow the red line, but because this one is here, this one adapts his behavior and deviates. So what kind of collective behavior kind of emerged from this? Well, surprisingly, there are many ones, not only one. The first one, we briefly talked about it, saw it before with Jens' talk, is something we call the formation of lanes. The formation of lanes is basically when you have 2 flows of people moving in the opposite direction, right? Then what you notice, almost systematically, is that after some time, the 2 flows will separate. And all those moving in the same direction occupy one half of the street, those moving in the opposite direction occupy the other half. Like as if the crowd would have decided to share the available space and say, okay, hey guys, we go there and you go there. Okay, so people share the available space. And this is something that is really easy to observe in field observation, right? Just put a camera in a commercial walkway and you will easily see that all those people moving that part, all those people moving the other direction. But we wanted to get some more quantitative details about this phenomena. So what we did is we have organized a controlled experiment. So we have a ring-shaped corridor like this one. We put people in there at random, but half of them are instructed to move clockwise and the other half are instructed to move in the opposite direction. And we just look at what happened. And we have periodic boundary conditions, right? Because they're just turning around. And what you see is that indeed, after some time, even in the lab, so that's quite systematic, you see that those people moving in the same direction, I mean, the lane formation emerged, right? Because these are data, we can also, we have, those white t-shirts they're wearing is a tracking system, so we can now see the same situation from above. And so it's empirical data, experimental data, and you see exactly, precisely what happened. And in the beginning, it's a bit chaotic, but after like 30 seconds or so, you see that we clearly have the segregation of the blues and the reds, right? One thing I want to say is that if you measure the traffic efficiency before this structure emerged and after that it has emerged, you see there's a clear difference. It's easy to observe. So the traffic efficiency is much better with that structure in place rather than before. So in a sense, you can say this is a smart collective pattern, because you just put people in a situation where it's kind of tricky to go ahead because they're all mixed and they move in opposite direction. And what you see is that after 30 seconds, they just self-organize in a way that everything is smooth, right? So that's kind of a smart collective behavior. But not so smart. What we have observed actually is that we did several replications, and what we have observed is that it's not systematic that those lanes appear. Sometimes they do appear and they are stable and it's all the best. But sometimes this is another replication, and what we see is that in the beginning it's all mixed up, and after about 20 seconds then we have a nice segregation between the blue and the red. And we're like, okay, done. But not, because after 20 seconds, what we see is that we have a breakdown of the organization. Everything is mixed again, and if you wait a bit longer, then you find that again the segregation happens. So we have kind of something unstable. The order emerges, and then it disappears, then it emerges again, and then it disappears, and this is more systematic than the stability. And what we have understood from the data is that it actually depends on the walking speed, the natural walking speed of the people that were composing the crowd, okay? So basically, if the majority of people have basically the same desired walking speed, we all want to walk slow, we all want to walk fast, okay? We have the same need. What happens is that we have this kind of phenomena with a clear segregation from the beginning to the end. But in situations where we have large inter-individual differences, so some people want to walk very slow, and some others, they want to walk pretty fast, then we have unstable situations. And the reason for that is very simple. It's just that if you're a fast walker and the structure has appeared, so you're now walking in the lane, you might be pretty upset because the average walking speed of the lane is lower than your actually desired walking speed. So what happens is you're just waiting for a moment where you can overtake. So you can walk at a comfortable speed, right? But if you have lanes, and if you overtake, then you end up facing the other flow, and you create this initial perturbation that triggers the a chain reaction, and then everything breaks down. But because the system is attracted by this structure, then the structure appears again until someone else tends to overtake, and then everything breaks down, and so on and so forth. So what we did then is we have organized another set of experiments. Now we want to know at the individual level what happens, how do people avoid each other, and how this collective structure can appear, right? So what we have done is like those, look on the left first, those very simple experiments, one-on-one, so just pairs of participants, and they are instructed to avoid each other in different situations, so both walking or avoiding static walks. And we combine this with field observations, but never mind. And this situation here on the right-hand side is pretty interesting because, well, basically when you need to avoid someone who's coming in front of you, it's a very simple coordination game, right? So you need to choose a side. Either you go left or you go right, right? And if we both choose a side, no matter whether it's left or right, then it's good because we can avoid each other and we can go ahead. But if we choose a different side, then we just bump into each other. So this is bad. This is what we want to avoid. So there's and in particular, it's tricky because the person you're facing, it's the first time you see that person, right? And you never probably see that person again. So it's a one-shot coordination game. It looks like it's just 50-50, and by chance you will do it. But no, what we have observed in those data is that actually 81% of the participants, they choose to go on the right-hand side, naturally, spontaneously. And this solves the coordination problem because there is kind of a hidden convention that says, okay, then if you're facing someone and you don't know where to go, then go on the right, because you have a great chance that the other one will do the same thing, and this will solve the coordination problem. So you have a convention there on top of the behavior that helps the coordination, and this is again like a simple heuristic, like just go right, it's likely to work. And in that case, we can talk again about car traffic because this is not fully related to car traffic. So it's true that some countries have right-hand side avoidance, like France, and some others have left-hand side conventions, right, like Japan and Australia and others. It's rather correlated with car traffic, but not always. There are exceptions, so it's pretty difficult in that case to say yes, it's directly connected. So we're basically unsure why we have those conventions. The main idea is that it's something you learn, right? So if you try at random 50-50, and if it's a success, then you do it again and again. And if everyone does this, then a convention emerged, right? And it's probable that the first thing you try in the first place is also correlated to the car traffic, such that there is a correlation, but it's not systematic. And in particular, in those countries where you have a lot of tourists, such as London, for example, you have the reverse. So people drive left and walk on the right. Okay, and I just want to show you this very simple simulation. So this is a computer simulation, and you implement some basic behavioral rule, but then there's a bias. So there's a slight preference to prefer the right-hand side for each individual, right? And what you see is that at the scale of the crowd, indeed, after about 30 seconds again, you see the split of the two flows. And again, you see that naturally, even without any will to do it differently, some people don't join, not immediately join the flow, because it's pretty difficult for them to, because there's the opposite flow as well. So you see, this is just a natural consequence of a simple avoidance, a simple biased avoidance. You don't need anything else. You don't need any top level rules. So basically, when you have a coordination failure, so you have those two people approaching each other, and for some reason they choose different sides. So maybe one is applying the convention, but the other one has seen like a wider space on the left-hand side. Therefore, they choose different sides and they approach each other. The thing is, in that situation, they have to take another decision, but super fast, because they're even more close to each other. They're even closer to each other. And now they have to decide again, okay, now should I continue or change? And what happens most of the time is that both change. So they're, again, in the wrong situation, and both again. And therefore you have those oscillations like that we kind of observe from time to time. We like to call them the pedestrian dance, because we usually look at video recordings fast forward motion, and when you see this is very it's very rare, so it's more anecdotic, but it's just a demonstration of this coordination failure. We're still working on the collision avoidance. There are other collective patterns that can emerge out of this. And one thing, for example, is something we call the fundamental diagram. So that's the relationship between the walking speed of the crowd and the density level. So how many people per square meter you have, right? And this is quite well known. It's very much used also in applied research, in applied studies. And that's basically that you have a situation at low density where everyone can walk at his comfortable walking speed, which is on average 1.3 for normal walkers. And as the density increases, however, you have a drop of the walking speed, and over here you have pretty much congested state around 4 people per square meter, which is quite high, right? So most of the situation we experience in daily life is between 0 and 0.5. So this is quite common, and it's very rare that we reach this level of 2, right? So this is the average thing, right? And the points are empirical data. So basically what you have is you have a Gaussian distribution around 1.3. So you have people who walk faster, people who walk slower, and the average is around there. So if you look only at the average speed, you get there. This is usually over there, the speed is very heterogeneous. So some people walk fast and others walk slow. And over here, it's very homogeneous. So you don't have much differences between walking speed, because everyone has to, because it's congested, has to walk at the same speed. What happens when you reach this threshold level here, precisely, not precisely actually, roughly, this density level here, is a new phenomena appears. So imagine you have a unidirectional flow now. Everyone is walking the same direction. What happens, spontaneously, without doing anything else, is a phenomena called stop-and-go waves. So stop-and-go waves is when people alternate between moments where they go ahead and moments where they stop, right? And this is a video recording from the Muslim pilgrimage in the Mecca. And it's obvious, now you have this coloring scheme, so you see that you have those waves, which is also a phenomena that you find in car traffic, right? It's exactly the same reason. It's just a delay in the moment where you start walking again and the moment where you slow down, which gets amplified at a certain density level, creates this. Now the question you can ask is, okay, but we have 4 people per square meter here, and we know what's going on, but this is not like the ultimate threshold. It may happen that it goes even farther, right? So the biggest, and I should say the worst, density level that we have observed was actually 9 persons per square meter. So you can imagine you have 1 square meter and you pack 9 people there. And this is usually like extremely dangerous situation. And this has been observed mostly in the Mecca during the pilgrimage, and every time we reached that density level, it was connected to dramatic accidents. And what happened actually is that when you reach that level, something else, another type of interaction takes place, which is the physical interaction. So people are not only trying to avoid each other, they are also unintentionally under the pressure of other people because the bodies are in contact, right? So you have these two things. I try to go there, but also my behavior changes because I'm being pushed by other people, right? And this phenomena is connected to other collective patterns. So what you have here is a video recording, a bit blurred, of the flow of pilgrims in the Mecca. Everyone is going from the left to the right. Okay, that's basically from the place where they stay to the holy place. And here you have a flow of people. And the same camera, the same day, but just a bit later in the day, that means as the density increases, because you have less people in the morning than later in the day, as the density increases, you see that this flow here is pretty smooth, and suddenly, at some point, then you see stop and go waves emerging, right? So nothing has changed in between, only the number of people there. And as things keep going on, then you have a new phenomenon, something we call crowd turbulence that emerge, which is characterized by the loss of directionality. So people are basically being pushed up, down, and sometimes backward also. And they also behave in mass. So your motion is deeply correlated with the one of your neighbors, but not necessarily to the one of those people far away. So you see it's kind of shaking. This is also why it's called turbulence, because it's a term from fluid dynamics, and it very much looks like sea under the on storm. And it's basically a matter. Here you have a video of the Love Parade in Duisburg. It's a matter of waves. So it's basically amplification of pushing waves. And if you see from there, if you look here, you will see a wave. Here it comes of pushing behavior, and then it hits the wall, and then it comes back, and you have waves almost everywhere. This is what we call crowd turbulence, right? And this phenomena is extremely dangerous. So that's the ultimate thing that we need to avoid, right? Because for two reasons. First of all, because the density is extremely strong. So people are, the majority of people, they die from asphyxia because it's too dense. And the second reason is that if you fall, if you can't stay on your feet, then other people, they don't control their movement neither. So it's not deliberate, but they will step on you basically. And that's basically what needs to be avoided. And that's just the amplification of pushing behavior, right? So even if everyone wants to be nice and helpful, then you have nothing to say because it's mostly about the physics of the system. People start pushing, the pushing goes from one person to another, hits the wall, comes back, and then you have those waves. And if two waves cross each other, then it's dramatic. So that's kind of things we try to avoid. And like a simple fundamental diagram could look like this. So it's basically that you have a smooth flow here, then suddenly stop and go waves appear. What we usually tell the managers is that this stop and go waves is a very useful pattern because it's not dangerous, but it gives you an indication of the density level. So if you see stop and go waves, basically try to do something to come back in this green zone. Otherwise, you're likely to get in this one and therefore in this one, right? So that's basically the kind of collective patterns you could observe. There are many more kind of interactions in crowds. I will not review all of them, but I will just tell you that it exists. The next one, for example, but I'm not getting into the detail, is a social interaction. So social interaction is basically when people are walking together, like a group of friends or something. So in that case, we're not really following each other. We work together. We're not avoiding each other, not really. We do something else. We try to stay together and work in a certain configuration. So that's also very interesting to study. Another form of interaction, which is very interesting, is the indirect interaction. So that's basically when you change your behavior as a consequence of the behavior of someone else who's not there anymore, right? So the thing is that other person has printed something in the environment, and you see this trace in the environment, and then you respond to it. And by responding to it, it's likely that you print something else in the environment yourself, and that other people behind you will respond to it. And this is how self-organized trails often appear or emerge in grassy areas or snowy areas. It's even faster in snow. Another kind of interaction. And the last one I'm not talking about neither, or maybe at the very end, is panic. So panic again is something else. It's not really about imitation. It's not really about avoidance. It's when, I mean, it's pretty unknown. This is why I'm not clear here. I say change of various behavioral variables. So basically, it's the idea is when you get panicked, you tend to behave in a different way. You tend to walk faster. Basically, you start running, or you communicate your panic to other people, and you tend to imitate others much more often, which is pure assumption. So because it's very difficult to observe panics, and panic is usually one first reason why people would aggregate in a certain place because they are all rushing to the exit, for example, which creates as a chain reaction like the phenomena of turbulence that we've seen before. Okay, so I'd like to talk about modeling. Okay, 20 minutes. Okay, so we did some review of empirical things. Now I would like to talk about modeling. So what's the best way to describe people's behavior, pedestrians' behavior, in a way that we can reproduce like this whole range of collective behaviors that we have observed, right? Well, the existing literature says you can work with a framework that comes from physics, right? So that's what the most common modeling approach that exists. So it basically says, and this is what Dirk Helbing does and did in the past 20 years, and Dirk Helbing was my PhD supervisor, so I was very much into this domain as well in the beginning, and then we try to develop more novel things. So the idea is, okay, let's assume just by now that a pedestrian in a crowd behaves just like a particle in a gas, for example. Having this assumption, now we can use all the tools from Newtonian mechanics and say, okay, now we can apply it to the pedestrians because we have assumed that they behave like particles, right? And for that, it's based on forces. A force is something that pushes the particle in a certain direction. So we can say, well, we can implement a driving force. Is like when the pedestrian or the particle, now it's the same, is alone, then moves in a certain direction. This is my micromotive, my intention. We can implement some repulsive forces like pushing this pedestrian away from others. We can implement some wall repulsion like pushing this pedestrian away from the walls. And at any moment, based on Newtonian mechanics, we can just sum up the forces and we get the acceleration of that pedestrian from which we can derive the speed, from which we can derive the position. And from that, this is a model. The only thing is, I mean, it's pretty complicated. One thing is also we assume something that is not really realistic, right? So we assume that, first of all, each pedestrian, for example, this person, has a complete information about his environment. So you know precisely where are the other people, where they move, and where they're going to be in the future, where are the obstacles, and you even see those people behind you, right? So you have full information, full knowledge of your environment, which is not so realistic. And then you put all these interactions into equation, then you have a long equation, and then you solve the equations, and then you make the next step, right? So that's not really realistic. And you do this like 10 or 100 times per second. Right, okay, so it's obvious that it's not so realistic, but it does work pretty well, actually. So one thing we did early in my PhD was, okay, we want to build a model based on that framework that would be the most reliable, as reliable as possible. So we just use all this data that we have collected, I showed before, and we try to combine all the information we have to derive the equation of this repulsive force in a way that we will have like reliable simulations. And the equation that we came up with is this one, right? So it's just a combination of my speed, my neighbor's speed, my position, my neighbor's position, my acceleration, my neighbor's acceleration, and then you combine everything and you extract this equation of motion. And it turns out that this is, when you put it in this model that I'm talking about, works very well. So you can predict pretty well how people will behave, or at least how the crowd will behave, just by implementing this, right? So the only thing is, it's on the one hand, it's very complicated. So at some point in my PhD, I had this feeling that I was losing control on the model because it was so complicated. I knew that the equations were there, so I was just injecting data and got the outcome and working with the outcome. But what happens between, I was unsure. It was like working like a black box. It was like really complicated. So that's something. So that's a feeling you don't really like, right, as a researcher, because you don't understand anymore what's going on. It's too complicated. But the prediction is good again. Yeah, but I mean, it depends what you want to do. If you want to predict well, or if you want to understand the behavior. And the other thing is, well, we keep in mind always that this is just an analogy, right? It's not really how things work. So maybe we could come up with another approach that would be simpler, maybe, and get the same outcome, the same results. And this is basically the moment where we came into this area of psychology and simple heuristics. And we basically try to develop like a heuristic-based model of pedestrian behavior that would be maybe simpler and yield the same quality of results. So to do this, we needed to ask two questions. The first one is, okay, what kind of information precisely does a pedestrian use when he's walking? Okay. And the second is how this information is processed to adapt the behavior. If we can answer those two questions in a realistic way, then we maybe come up with a model that is simpler. And also because we do this every day, it doesn't look so complicated, right? So maybe there's a way to do it simpler. The first big step in the model is to change something. Well, so far we have this view from top, from above. We have a top-down view, assuming that this is the pedestrian, alpha, and these are the other people, and we just try to think of how we could combine those different interactions. But this is not the real outcome, the real input. Sorry, this is not the real input when you have as a pedestrian, right? The real input is rather something like this, right? You see the situation from your first-person perspective, right? And this is exactly the same. From there, from this situation, it's not obvious where this blue point should go to reach this red star, right? Maybe over there or something. But if I give you this input, right, now it becomes super obvious where you should go. You should go here, right? Because we're used to this kind of information processing in our life, so it makes this thing more easy or easier. And why should we go there? Well, because this is obviously the biggest empty space, the widest empty space. So there's something to do also with empty spaces in the model. And this is what we do. So the first thing is we formalized this kind of situation in a mathematical way. So this assumes a lot of simplifications. So this function here, f, is basically describing the distance that you can walk before a collision occurs. So 0 is right in front of you, and positive values is on your right-hand side, and negative values are on your left-hand side, okay? So that's your vision field. And this is how far you can go before a collision occurs in this situation, for example, right? And so that's the input. Here we have a formalization of the input. And now that we have this, we just have to define some rules. Okay, how do you use that to adapt your walking speed, for example? Actually, we need two things. We need two rules. Because there are two components in the movement. The first one is the direction, and the second one is the speed. So we needed two rules. One is using the visual input to adapt the walking direction, and using the visual input to adapt the walking speed. We came up with some rules, but surprisingly, many of them worked pretty well. So we basically don't know which one to take, so we just took a pair of rules that worked pretty well and just used them. The first one is basically you choose the line, you choose the sight line that comes closest to your destination point, right? So among all your vision field, you have different depth, right? And you take the one that comes closest to your destination point. You just pick it and you go there, right? Very simple. For the walking speed, it's a bit more difficult. We had to inject one variable, which is the only variable of the model, which is the reaction time of the individual, right? So we say that the reaction time is basically how much time you need to stop your movement if in case of an expected encounter. So we call tau, and it's usually half a second. So let's take this variable and say, okay, now I just adapt my walking speed in a way that I'm always farther than my reaction time to the closest individual. So if anything happens, I have time to stop, right? So if I'm too close from the person in front of me, then I just slow down such that that person in front of me is always half a second away from me. That's two possible rules. I said there are many more. Then you can combine them in a very easy way. So that basically just says that I decide where I want to go, I decide how far I want to go, and it takes half a second to adapt to this position, right? And using this model, well, this is the simulation I've shown before, and it actually works pretty well with different patterns. So this is the red line, the prediction of the model. This is some predictions on the one-on-one interaction, and we also have lane formation and things like that. The only problem came when we started to push the density level. So we wanted to know, okay, now let's take the model, it's great, and let's take it to predict extreme density situations. And when we did that, it didn't work, right? And why did not? And what the problem precisely? The problem was it's not the same kind of interaction anymore. So the heuristics that we have here, they are very well suited to describe avoidance situations. So that's what I talked about in the first place. But it's completely hopeless to describe physical interactions, and that was the problem. So we have a situation like this, and in that case, the model we have works well. But if we have a situation like that, then any heuristic can never predict that this guy will be pushed away by this one, because this is just physical consequences, right? Because they're touching each other. So actually the solution came from combining both. We use simple heuristics in case where we don't have any physical contacts between people, but at the moment where two people start touching each other, then we use repulsive forces from the physical model. But this is not an analogy anymore. It's real physical force because people are really touching each other, right? And as soon as they don't touch each other anymore, then we use the heuristic again, right? So it's combining the two things that made it possible some more simulations are extreme densities. So I can show you this small movie here, for example. This is a simple evacuation scenario. Here you have a simple evacuation scenario. This is the model at work, and this is pretty high density level, but here you have like basically combination of heuristics to find out the exit and navigate, and repulsive forces to solve the pushings between people. And the model, for example, allows to derive some things on high density situations. Here, for example, you have a straight corridor with a small bottleneck, okay, and this is the direction of motion at high density, and the colors indicate the places where the physical force is strongest. Right, so that's basically the place where you don't want to be, because this is where the physical contacts are stronger, and it's no surprise, but it's on the edge of the bottleneck over here. So this is the place you should avoid. And same situation where you have a straight angle, then you don't want to be there. Okay. And okay, so I will take the last 10 minutes just to tell you a bit about my ongoing work. So this is more about a methodological issue. So I mean, one thing is that it's pretty difficult to study crowds and collective dynamics in general, because basically you have three possibilities to do your work. You can do field observations, right? So you can basically go in the street, have a video camera, and do some recordings, and then analyze the recording. The only problem is, first of all, you have no control on the data, so many things may happen that you're not controlling. And the second point is that you need a tracking system that is pretty difficult to set up. You need to track the people on the video recording, and that's really painful. So what you can do then, if you need a control on your system, is do controlled experiment. That's what we do here in psychology. But that's possible because we work only with one or a pair of participants. But when you want to do it with a crowd, you need to collect, you need to hire like 100 participants, and you need to rent a gymnasium, and you need to set up a tracking system on the walls. For example, for that experiment, the tracking system was worth about 50,000 euros. So, right? So it's super expensive. And if you want to change the condition, then you have to move a wall. Like it's not that easy, right? And it's always super difficult to work with 100 people. I mean, this one, for example, we took about 6 months to set up, and it's hard. People are always late, and you have to manage the crowd. And when everything is ready, and one raises hand and says, "Oh, can I go to the bathroom?" And like, "Come on, okay, go to the bathroom, but come back quickly." And so it's very difficult, right? And I don't think I want to do this kind of experiment anymore because it's too difficult. And the last solution is to do computer simulations, right? But computer simulation is super nice because you can change whatever you like. You can change the environment. But you need to have a reliable model, right? Otherwise, you're not sure exactly what you get. Sorry, I got some water. And so from these three methods, none of them seems to be particularly perfect, right? So what we do usually is we do computer simulations, from which we derive predictions. Then we go to controlled experiments, but that's pretty hard. Or we can go to field observations, come back to simulation, and we do loops like this. And but one day we came across this paper here. It's completely different story. Maybe some of you know about it, right? So that's a study of collective behaviors, again, by Salganik, but mostly people around Duncan Watts. And what they did is that they study collective behavior, so that they have the same issue, right? They can do lab experiments, but it's difficult. They can do simulations and so. And they came up with this new method, which I found it revolutionary. So they do online experiments. So that's basically, they set up a virtual place. In that case, it was a market, right? Cultural market. It's completely virtual, right? It's a website somewhere in the air. And people connect to it they are from home in front of their computer, right? So you can have hundreds or thousands of people. It's easy to synchronize people. And then they do their experiment, whatever it is. They can easily change the conditions because it's a virtual place, so it's just a matter of setting parameters, and you see how people interact with each other in this virtual place, right? And this was a very nice project, and it led to many, many different other things working on the same way, like study of social networks, study of propagation of innovations, and things like that. And then we came to the crazy idea, okay, but can we do it just for fun? Can we do it with pedestrians as well? So like, we have a crowd of pedestrians, and they meet up in a virtual place, right? So that sounds pretty strange, but this is what we try to do at the moment, and it's not yet working. But it's because it's pretty difficult. So basically, at the moment, we're just doing endless pilot experiments again and again because we need to set up many details of it. The idea is, we do it in the lab at the moment, but ultimately we want to take it online. The idea is we have, say, 30 or 40 participants, and they're in the lab, and they're all sitting in front of a computer, and all the computers are connected to the network, and all these people, they control the motion of one particular character with a first-person perspective, but they are all in the same place, okay? They're all in the same virtual environment, so you can see the other participants, right? I show you some demonstration. So this is basically what you see when you're a participant. This was still like a preliminary version of it. And the control you have is basically, with your mouse. You can move the mouse left, right, and you see what's on the right-hand side. You can move the mouse to the left-hand side, and you see the other direction, right? And the mouse, you combine it with the keyboard. So now if you press the forward key on your keyboard, you just move forward, like this. Okay, you just move forward, right? And so the video is a bit shaky, but in the computer it's super smooth. It works very well. Now what happens if you move like this in a virtual place, but you meet other people? The question is, can we reproduce things that we know actually? And if that's the case, then it would make the situation, the research much, much easier, because then you can test different settings, you can test different things, but all in front of your computer. What we're trying to do at the moment is to replicate this. So this is an experiment from a colleague, Tobias Kretz, and he did like a simple evacuation situation. So he put people in the room, and everyone is instructed to evacuate the room, and they give the starting signal, and people start to move outside, and they vary the door size, and they got this curve here, right? This is the door width, this is the evacuation time. So at the moment, we're trying to reproduce this curve with this situation, but in a virtual place, right? I show you what we have. So we did it already. We did several pilots. So this is a video. So we have the same number of people, the same room size, the same door size, and we want to know how long they take to evacuate. Again, each people here is a real person sitting in front of a computer, right? And can see the other people, right? And this is like the dynamic that we observe in this virtual environment. The biggest issue we have at the moment is to make the control system so intuitive that people like this one will not be kind of lost. All right.
You always have drunk people.
You always have drunk people. But now this was like a couple of months ago. Now it's super smooth because we made it super intuitive. I mean, you can see exactly the same situation seen from inside, because now you can put the camera wherever you like, right? And this is the same situation seen from the perspective of one participant, right? So you're just in the middle of the crowd and you're trying to evacuate and you try to move outside from the room. And again, each single guy here is controlled by a real participant. So there's no model, there's no assumption, right? It's just real behavior. And here you get, so again, it's shaky, but in real time, in front of the computer, it's pretty smooth.
So basically what the subjects are facing is basically playing Call of Duty but just going forward with the computer. It's
Yes.
like a video game. I mean, they control the keyboard.
Yeah, it's the engine of a video game that we're using here. So it's just like a video game. I show you. I have a last slide, and then we ask questions. Okay. what we have at the moment is this. This is the curve we have in the virtual environment for door width versus evacuation time. This is data in blue points. So it's very positive because we have roughly the same trend. Just the scaling factor is in between, which is very nice. I mean, a scaling factor is super easy to correct. And we're still doing pilots. I mean, we've been doing pilots for 1 year now to make it smooth. And I don't show you the video on the top. And then the idea is, okay, first of all, we're gonna reproduce all the collective patterns that we know in this virtual place just to make sure that it's reliable. We're gonna do lane formation and other things. And only after we will start to ask very interesting questions, such as panic situations, for example, something you can never observe in real life. You cannot do experiments with panics, right? It's just impossible to have a camera recording with a real panic, but now you can set up whatever you like. You can have fire, you can have people dying. Okay, it's virtual, so you can really test things like that, and you incentivize your participants based on the survival rate, so they really want to do it, right? So it can solve many problems. So I've been talking for 1 hour, so I stop now, and thank you for your attention.